discussed about isomerism. Okay. So what is isomerism? Can anyone tell me what is isomerism? Yes, what is isomerism? So we have discussed in the last class what is isomerism and the different types of isomerism, right? So what is isomerism? So two or more compounds when they have same chemical formula, but the arrangement, okay, the atoms arrangement is different, because of which its physical and chemical properties also change, right? So they are called as isomers, and the phenomena is called as what? Isomerism. Okay, and the phenomena is called as isomerism. So this was about isomerism. Then we have discussed two types of isomerism. The one was structural isomerism. The second is stereoisomerism. Structural isomerism means what now? Yes. What do you mean by structural isomerism? They are having same molecular formula but different structural arrangement of ligands around the central metal atom. Okay, so they are called as structural isomerism. So in structural isomerism, we have seen four types: linkage, ionization, coordination, and solvent. And we have seen the examples also. Then we had discussed about stereoisomerism. What do you mean by stereoisomerism? Yes, the spatial arrangement. Okay, so same molecular formula, sorry, same chemical formula, but the different arrangement, different spatial arrangement. Okay, so because of the different spatial arrangement, it will show stereoisomerism. Okay. So now in stereoisomerism, we have discussed yesterday geometrical isomerism, right? So geometrical isomerism and optical isomerism, two types are there. We are going to discuss what geometrical isomerism. So what is geometrical isomerism? So the isomerism, it arises due to the different arrangement of ligands around the central metal atom. Okay, then this gives rise to geometrical isomerism. Got it? Okay. So we know that, so whenever we have heteroleptic complexes, what do you mean by heteroleptic complexes? When you have more than two types of or more than one type of ligands present in the complexes, then such complexes are called as heteroleptic. So if the ligands are on the same side, okay, that is on the adjacent side. Let me tell you, if the ligands are on the same side or they are said as adjacent side, then they give rise to cis isomer. Give rise to what? Cis isomer. If the ligands are on the adjacent side, okay, if the ligands are on the adjacent side, then it gives rise to trans isomer. So we have seen the isomerism of geometrical isomerism in coordination number 4. So this we have discussed yesterday, right, of coordination number 4. So next, okay. So this was the another type what we had discussed, A, B2. Uh, so here you can see we have a example. So what we can see here, geometrical isomerism, here we can see what? So we have a platinum, okay, diamino, uh, dinitropyridyl platinate, diamine, that is platinum. Okay, so bromo, platinum. So it is platinum is there. Then diamine means two amino. Then one more bromo. Then chloro. Okay, so A2BC type of ligand is there. Okay, so let us discuss this later with the example itself. Okay, so this we have discussed today. Okay, so the next we are going to discuss is about the geometrical isomerism in coordination number 6. Okay, coordination number 6. Coordination number 6 means what? What do you mean by coordination number 6? The number of ligands around the central metal atom, they should be 6. Okay, then this gives rise to what? Coordination number 6. Okay, so the metal is there in the center and how many ligands are present? Okay, so these are 6 ligands. So 6 ligands are present means the coordination number of the central metal atom is 6. So in heteroleptic complexes, how we will get coordination number 6? Heteroleptic means two types of ligands should be there. So X2 and L4. Okay. So two types of ligands are there, X2 and L4. So here they have given A4 and B2. Anything you can take. Okay. So let us consider this only. So M is there. One ligand A is 4 and B is 2. So how many ligands are there? 6 ligands are there. So it gives rise to coordination number 6. Okay, so here, what you can see, we have two types of ligands. One is B ligand. Okay, these are 2, and A ligand, which are 4. Okay, so how we are going to? So we'll take one example: cobalt, NH3 4, and Cl2. So let this be the example. Okay, cobalt, NH3 4, Cl2. So you can see now how the arrangement is there. Cobalt is in the center because it is a central metal atom. NH3 4, NH3 at 4 corners of the square planar. Okay, square, and 2 Cls at the axial position. Okay. Now this is, so this gives rise to trans. Okay, this gives rise to trans because they are opposite to each other. Because they are opposite to each other. Now here, so how do you write the cis configuration? Or okay, cis configuration. So all are at a side. Okay, one side. So these are at one side. Okay, these are adjacent to each other. Okay, these are all adjacent to each other, because these are all adjacent to each other, and two Cl atoms are, okay, here they are, and these are all adjacent to each other. So this gives rise to cis isomer. So whenever you have 6 coordination, okay, so that time this is the way you are going to represent your geometrical isomerism. Okay, so metal will be in the center. So A type, okay, which are 4 in number. So if you write like this, and the B types like this, so this gives rise to trans isomer. That M and all the, so A types on one side, that is on the adjacent side, and B types on one side, then this gives rise to cis isomer. Is it clear? So this is the coordination of the, so important. Okay, they can ask you. Okay. Let us go for the next one. Next type of ligand in coordination number. Okay. One more example here. Before that, let us see with a, okay. Okay, so before that, let us see B type. Okay, so we have seen first type was A4B2. Now second time is MX2LL2. Okay, so this is a bidentate ligand. If you have a one of the ligand is bidentate, another is a unidentate ligand. Okay, so let us take an example. So let me take the examples of cobalt, Cl2, ethylene diamine twice plus. Okay, so how will you represent this now? So again, cobalt will be in the center, cobalt will be in the center. Then, okay, then, so we are going to write cis and transform, right? We are going to write cis and transform. So again, cobalt in the center. Okay, so when the ethylene diamines, okay, so if there are side to each other, okay, if they are adjacent to each other, so here one will come, here one will come, 6, right? So now here beside this, again when ethylene diamine, here 1 Cl, here 1 Cl. Okay, so here what you'll get? So what is this? So this is a cis form. This is a cis form because all are adjacent to each other. Now, if I write your transform, okay, they should be opposite to each other, right? So these are opposite to each other. Right, these are opposite to each other. So this is a transform. So whenever we have what? So whenever we have X2LL2 type of ligand, that is whenever you have a one is your bidentate ligand and another is the monodentate ligand. Okay, so these are the examples. Is it clear? So this is a second type. I hope you are noting it down. Yes. So how will you represent the that is the complexes when you have a coordination number 6 and with the type of this. Okay, that is one of the ligand is what? A monodentate, another is a bidentate ligand. Is it clear? So please note it down. So this was the second type. Now we will go for the third type. So third type C. So whenever you have M, A3, B3. Okay, so two types of monodentate ligands are there. One monodentate ligand is 3 number and the second one is 3 number B. Okay, so let me take an example of cobalt. Okay, NH3 thrice and NO2 thrice. So this is the complex. Okay, this is the complex. So write the so again, cobalt in the center. Okay, cobalt in the center. So when you have the okay, so this is one arrangement possible. Okay, this is one arrangement possible. Second arrangement. So take this down. Okay, so this is another where NH3 are opposite to each other. Okay, and NO2, and here one NH3, and here one NO2. Okay. Now here, what is the possibility? Okay. Now here you can see that. Okay. So here, when you have MA3, B3 type of this, so that time it gives rise to different. So you'll get here, you will see something called as facial arrangement and meridional arrangement. Okay. Meridional arrangement. So whenever you have MA3, B3 type of ligands, okay, in the coordination number 6. So when you have this type, okay, complex, so that time you are going to see something called as facial and meridional. Okay. Now here when you see at this particular position, when your nitro groups, okay, you can see that the nitro groups are like this. Okay, how they are placed in one form. Okay, so one side. So let me mark it first, then I can explain you. And here you can see that the nitro group, okay, these are at one position like this. Okay, so now how will you explain this? Okay, so uh, so whenever so this type of so another type of geometrical isomers. Okay, so whenever you have mx6, so what type of geometry it will show, students? Yes, whenever you have L6, that is metal is there, and 6 ligands are there. So that time what type of geometry it will show? Yes, what type of geometry it will show? It will show a octahedral geometry, right? It will show a octahedral geometry. Now in this, so whenever geometrical complexes, okay, when you have a octahedral geometry, that is when you have a coordination number 6. So in coordination number 6, okay, whenever you have such complexes, it will show octahedral complexes, and that is of the type MA3B3. Okay, of the type MA3B3. Then if all the three identical ligands, if they occupy the adjacent position, so if the identical ligands, so these are the identical ligands, right? 1, 2, and 3. So if all the three identical ligands, if they occupy adjacent position at the corners of the octahedral, then it is termed as facial arrangement. So this is a facial arrangement. So these are so all the identical ligands are and they are what positioned at one side of the corner of the octahedron. Okay, so they are termed as facial isomer. What they are termed as facial isomer. Then second is what? And if the position or occupied at the meridian of the octahedron. Okay, so this is a meridian position. Meridian. Okay, so if they are occupying the meridian of the octahedral, then they give rise to what type of this? It gives rise to meridional isomers. Okay, so this gives rise to meridional isomers. So whenever you have MA3B3 type, so they will show facial and meridional arrangement, not cis and trans. Okay, so facial arrangement means what? The identical isomers are occupying the adjacent position of adjacent corners of the position at the corners of the octahedral. Okay, so facial isomers and what is meridional? If they occupy around the meridian of the octahedral, then they give rise to meridian isomers. So this is the meridian position. Okay, fine. So this completes our geometrical isomers. Okay, so this is the geometrical isomers. So this was the example. One more example. Okay, see here, M A3, B3 type. Okay, so chromium is there, and three Cls are there, and NH3s are also three. So this is what M is there, A3 and B3 type. So what will happen? So chromium will be in the center. Okay, and so like this is the octahedral shape. So if the NH3s, okay, take NH3 at one side and take CLs at another side. So if the so if so this arrangement, okay, when the ligands are arranged at the what? At the meridian position. Okay, sorry, at the adjacent position of the octahedral, then this gives rise to what? This is your, so this is your what? This is your facial isomers. Okay, these are your facial isomers. So you can see that the identical ligands are at the adjacent position at the corners of the octahedral. Then another arrangement is what? Metal in chromium is in the center. Okay, chromium is in the center. Then when what? NH3, NH3. Okay. Then your NH3, Cl, Cl, Cl. Okay. So here what you can see. Okay. So now here what you can see here, your your this. Okay. So they are occupying at the meridional position. So these are meridional isomers. Okay, so they are occupying the meridional position. So these are the meridional isomers. Okay, fine. So this is about your geometrical isomers. So in geometrical isomers, we have seen three types. Okay, we have seen three types. Okay. Now let us go for the optical isomerism. Okay, what are optical isomerism? So complexes having identical chemical and physical properties. So they are having same, what they are having identical. Identical means what? Same. Okay, same chemical and physical properties. Okay, so their physical and chemical properties are same. So where it differs then? But it differs at, okay, it differs only in direction of rotation of plane polarized light. Okay, direction of PPL, that is plane polarized light. Then they are called as what? They are called as optical isomerism. What they are called as optical isomerism. Okay, so whenever the complexes, okay, so complexes having identical, that is chemical and physical properties, but where it differs in only the rotation of plane polarized light. Okay, so such complexes, so they are called as optical isomers, and the phenomena is called as optical isomerism. Okay, the phenomena is called as what? Optical isomerism. So this was about your what optical isomerism. Okay, so so whenever the complexes are having same physical and chemical properties but differ in the plane polarized light. So that time they'll give rise to two types of isomers. Okay. So two forms of isomers are possible. So one is the dextrorotatory. Okay. One is a dextrorotatory and the another is the levorotatory. Okay. So two possibilities are there. So whenever you have optical isomers, now if you take two of your palms, okay, and if you take the mirror image, okay, if you take the mirror image of that and if you try to impose on one another, is it superimposable? No. So these are the optical isomers. So what are optical isomers? So optical isomers, or they are called as the stereoisomers, or they are called as the enantiomers. So these are mirror images of each other. Okay, and these are non-superimposable mirror images. Means what? If you take the mirror image of your palm and if you try to put your thumb, do not coincide on your thumb. Okay, so they are non-superimposable mirror images. So stereoisomers, which are non-superimposable mirror images, they are called as enantiomers. Okay, so here two types of possibilities are there. So let us discuss. So what is dextro then? If the plane polarized light, if it is turned to right side, okay, if the plane polarized light is turned clockwise, okay, you can say if it is turned clockwise, then it gives rise to dextro-rotatory. If the plane polarized light, if it turns to left hand side, okay, or in anti-clockwise direction, then it gives rise to what? Levorotatory. Okay, left side, not light. So left side. So it gives rise to levorotatory. Okay. So let us see front. So in this two types are there. So one is when you have a coordination number, uh, this, okay. Let me take a blank slide. So there are two possibilities. The first possibility is there tetrahedral complexes of the type M, A, B, C, D. Okay, so whenever you have four different ligands, monooriented ligands, these are optically active. Okay, these are optically active. Then the second example is what? Optical isomerism. Okay, it is common in your what? Optical isomerism is common in octahedral complexes. So in octahedral complexes, you can find the optical isomerism. Okay. So the first possibility is involving your bidentate ligands. Okay. So if you have the type, so if you consider a type of M, AA3. So what it means? So this is a octahedral complex. Octahedral complex means coordination number 6. Okay, coordination number 6. But you have a bidentate ligand. How many bidentate ligands are there? 3. So 3 bidentate ligands means, okay, 1, 2, 3. So 1, 2, 3, 4, 5, 6. Okay, so it can get attached to the central metal atoms to 6 corners, right? So this is a one type. Whenever you have M, okay, AA3. So we have a bidentate ligand. Okay, so let us take an example. So example is cobalt, ethylene diamine. Okay, triethylene diamine cobalt. Okay, so this is the example. So let us write uh, yeah, dextro and revo rotatory for that. So cobalt is in the center. Okay, so octahedral geometry means 1, 2, 3, 4, 5, 6. So one ethylene diamine here. Okay, one ethylene diamine here, one ethylene diamine here. Okay, and one ethylene diamine here. Okay, so this is the arrangement of ethylene diamine. So let us write so this is your octahedral complex. So this is what? This is a dextrorotatory. So this is a dextrorotatory of your uh, the complex. Okay. Next is cobalt. So this is on the right hand side. So you can see that the half part is on the right hand side. Right. So this is on the right hand side. So this is a dextrorotatory. So let us see the next one. Cobalt. Okay, so one ethylene diamine here, another ethylene diamine here, another ethylene diamine here. Okay, so write the possibilities. So, okay, now here what you can see. Okay, so what you can see here. Yes, what you can see, students. So here the half of the side. Okay, here this is on the left hand side. So this gives rise to levorotatory. This gives rise to what? Levorotatory. So this is the one type. So type 1. Okay, whenever you have a bidentate ligand, so the number of bidentate ligands are what? What is bidentate ligands? When you have two donor atoms, right? So ethylene diamine, it is represented by this. Okay, that is CH2, CH2 is there, and NH2, NH2 is there. From this N, it is getting linked. So we represent like this direct, okay, because it is very difficult to write this much atoms here, right? So in simple way, we are going to write En, and we are going to link like this. Got it? Is it clear up to here? Yes. Any doubts up to here? Any doubts? So we have seen type MAA3. Okay. So where you have a bidentate ligand involved in the octahedral complex. Okay. So let us go for the next one. Second type. So we have one more type. So type MAA2B2. So here what you have here, or you can consider it as MLL2X2. Okay, what is it? So you have a bidentate ligand which are two in number. Okay, bidentate ligands are two in number, and your monodentate ligands are two in number. So bidentate ligands are two in number, and monodentate ligands are two in number. So total coordination is what? It is 6. So platinum, Cl2, and ethylene diamine 2. Okay, so this is the example. So let us consider the example and write the. So in this, what is possible? Yes. So let us write. So platinum in the center. So write the octahedral. Again, platinum in the center. Okay. Now here, so we are writing this, right? So if you write En and one more En this side, here Cl, here Cl. Okay. So what you can see here? So these are your dextrorotatory. So this is your dextrorotatory. Okay, this is your dextrorotatory. Then Cl, Cl. So this is on the left hand side, right? So this is on the LHS. Then ethylene diamine and ethylene diamine. So this is your L. So this is your L isomer. Okay. So ethylene diamine. So this is your what? L isomer. Okay. So L. So this is a dextrorotatory PtCl2 ethylene diamine twice 2 plus, and this is a levorotatory Cl2 ethylene diamine 2 plus. Got it? So this is the second type. Okay, so when you have, so this is levorotatory, that is a plane of polarized light is turned to the left hand side, and here the dextrorotatory where it is turned to the right hand side. Okay. So you have to write so this completes our isomerism. Okay, this completes our isomerism. Now let me give you some examples. You need to write the structures for this geometrical isomers. Okay, so write the geometrical isomers for this. So geometrical isomers means you have to write the cis and transform. Okay, tell me how do you write for this? And second possibility is FeNH3 twice CN4 minus 1. Yes, please tell me how do you write the geometrical isomers? Geometrical isomers means cis and trans for your for your tetrahedral complex, square planar complexes, and facial and meridional for your what is that? Octahedral complex. So this is of the type MA2B2, right? MA2B2. So this is a square planar complex. So write the what is the possibility, students? How do you write? So which is our metal? Our metal is platinum. Our metal is platinum in the center. Then, so at the four corners of the square planar. So if I write Cl at one side and NH3 at another side, what is this form? Yes, what is this form? Tell me. And what is this form? Yes, very good. BB has answered it correct. This is a cis form. Yes, first one is cis form. Yes, first one is your cis form. Okay. It is your cis isomer. Then second one is your trans isomer. Yes, very good. Yes, Yamuna has also answered it. It is a trans isomer. Why? Because the identical ligands are at the opposite side. Okay, they are opposite side. And here the identical are at the adjacent side. Okay, fine. Next one. Next for Fe. So I'll write first and you have to tell me. Okay, so Fe. So octahedral. So this is of the type Ma2B4, right? We have Ma2B4. So this is a octahedral complex, right? This is a octahedral geometry because we have a coordination number 6. So the possibility is what? The possibility is we are going to have a octahedral complex. So Fe in the center, 1, 2, 3, 4, 5, and 6. So again, Fe in the center, 1, 2, 3, 4, 5, and 6. Okay, let us write the atoms now. So one possibility is that if I write all the CN atoms at one side, 4, okay, and NH3 here, NH3 here. So this gives rise to what? So these are all at one side of the octahedral corner, right? So this is what? This is your cis isomer. So this is your cis isomer. Yes, very good. Yamuna has answered it. Then second possibility is that, so CN, 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 and CN. Okay. And NH3, NH3. Yes. Can anyone tell me what is this? This is a, yes, very good. Yamuna has answered it. It is a trans isomer. Okay, it is a trans isomer because the atoms are opposite to each other, right? You can see that the atoms are opposite to each other, right? So these are opposite. You can see, right? So this is the trans isomer. Okay, is it clear? So these are the examples. So like this, they can ask you example. Now let us go for the one more. Okay, one more example. So out of the following two coordination entities, which is a chiral? What do you mean by chiral? Chiral? Chiral means they are optically active. Optically active means they have four. So this is a chiral molecule. What do you mean by chiral? Four different groups are attached to the central metal atom. So you have to tell which is a chiral. So A, first is cis CrCl2 oxalate 2 3 minus, and second is B, trans CrCl2 oxalato 2 3 minus. Okay, write the structures for these. The first one, cis, how it will be? So chromium in the center. Okay, cis means at the one side, right? Just see how do you write it. So oxalato and oxalato, then chromium, chromium. So this is one possibilities of your cis isomer. Okay, so this is cis or cis or D because it is on the right hand side. Okay, so this is on the right hand side. So it is D. Then if I write trans, if I want to write trans now, so what is the possibility? So chromium here, then ethylene diamine, ethylene, sorry, not ethylene, oxalato. So oxalato is also a bidentate ligand. Okay, oxalato, OX, OX. Okay, so here also the possibility is like this. Okay, so this is the possibility. Wait, let me write it properly. So chromium 1, 2, 3, 4, 5, 6. So chromium here one Cl, here one Cl. So oxide, oxide. Okay, chromium 1, 2, 3, 5, 6. So Cl, Cl, oxalato, and oxalate. Got it? So this is our D form, this is our L form. So the out of these two entities, your cis form, okay, your cis form or the D form is your chiral molecule. Okay, it is optically active molecule. So it is optically active. Fine. So is it clear up to yours? Yes. Is it clear? So this completes our isomerism. Okay, this completes your isomerism. Any doubt? So please uh, go through all the isomerism with examples. Very important, as I have told you from the last class where we were discussing about isomerism. So isomerism definition plus examples. Okay, they may ask you what is a hydrate isomerism. Give an example. So you should know all the isomerism with their examples. Fine. Okay, so this completes your isomerism. So next is your bonding. Okay, so we are going to see some theories. Okay, so that we shall be discussing in the next class. Okay, that is Werner. So the first one is the Werner's theory. So Werner's theory, okay, so we have different theories, how the bonding occurs. So next is VBT. Then we are going to discuss about VBT, that is valence bond theory. Then we are going to discuss about crystal field theory. Okay, so three theories are there. Okay, and so these are the, so we are going to see the application. Okay, what are the limitations? So this will take so little deeper it is, so that we will be discussing from tomorrow. Okay, any doubts up to your, so after after the classes you need to revise it. Okay, so if you find any difficulty you can ask me in the next class. Okay, fine. So please go through the things whichever I have told you, because it is very difficult to grasp in one thing. Okay, in one time you cannot everything you cannot understand. Okay, so you just read, go through the things. If you do not don't understand, you can ask me in the next class. Fine. So by this, I shall end the session here. Okay. So we'll meet in tomorrow's class.